During last lecture, we talked about relations, and now we have properties of relations. Here we have three properties of relations, which are reflexive, symmetric, and transitive. And if a relation has these three properties all together at the same time, it means that relation is an equivalence relation. First, we have reflexive relation. We say, let R be a relation on a set A. Then R is called reflexive if XX is in R. That means for all elements in A, we have a relation from any element to itself. For all elements in the set, we have a relation between a member of A with itself. Let's take an example here. Let A to be 1, 2, 3. If we have 1, 1, 2, 2, and 3, 3 in the relation, we don't care what else do we have for the reflexive. If we have 1, 1, 2, 2, 3, 3, that means if we have a relation from any element of A with itself, then we say this relation is called reflexive. This relation is called reflexive if we have a relation from any element of A with itself. So if we have no relation from one of the elements of A with itself, this is not a reflexive. This is not a reflexive. That means for every element in A, we must have a relation between any element with itself. Okay? And in the matrix form, we must have 1 on the diagonal. That means all elements on the diagonal must be 1. Yeah. If we have this matrix, we must have 1 on the diagonal. Even all of the others are 0, it's okay. Sorry. Even if we have numbers in the other elements, it's okay also. If the elements on the main diagonal is 1 or 1, we say this relation is a reflexive relation. In the diagram form of a relation, we say we must have a loop at each vertex. That means if we have a loop from any element, from any vertex to itself. Yeah. This for all representations of relations. As you see here, we have digraph and matrix form of relations. This is digraph. As you see, we have a loop at each vertex. And also in the matrix form, we have 1 at all elements on the diagonal. So this relation is called reflexive relation if it satisfies one of these. Or if you have a relation from any element with itself in the matrix notation of relation, of the relation. Now we have an example. In the example we have the relation R on the set X. Set X is 1, 2, 3, and 4. Is defined by X is less than or equal to Y. It's less than or equal to Y. We say every number is less than or equal to itself. Okay. Here we have 1, 2, 3, and 4. We say 1 is less than or equal to 1. 2 is less than or equal to 2, and so on for 3 and 4. Okay. We see the relation is this, and also we have some more elements. We have some more elements in the relation, but the most important thing here If you have a relation from any element with itself, that's enough for the reflexive. Okay, and also this is a relation on the set. Here we can take 1 and 2 because 1 is less than or equal to 2. 1 and 3, 1 and 4, 2 and 3, 2 and 4, and also 3 and 4. We have these all elements in the relation, but we just look for those elements which both both numbers in the element are the same. Look, 1 1, 2 2, 3 3, 4 4. We have no 5 5 and so on. Okay, because here in X we have no 5 5. That means for all elements in X we have 1 1, 2 2, 3 3, and 4 4. So you say the relation, this relation on the set X is reflexive. This is a reflexive relation, since for all X in X, X is in R. That's for reflexive. And also we have irreflexive. We have irreflexive. If you have no a relation from any of the elements with itself, we say that's irreflexive. That means we must have no relation between any of the elements in the set with itself. So for every X in A, we must have no XX in the relation. If a relation satisfies this condition, we say the relation is an irreflexive relation. In the matrix notation, we must have 0 for all elements on the main diagonal. On the diagonal, we must have 0 for all elements. In the digraph, we must have no loops at any of the vertices. Look at this here. If you have one loop like this here, we say this is not an irreflexive relation because at this vertex we have this loop. So we must have no loops at any vertices. That's for the digraph. And for matrix, we say all elements on the diagonal must be 0. All of these must 0. Then we say the relation is irreflexive. If at least one of them is 1, we say that's not an irreflexive relation because here we have this element which is not 0. And also we have not reflexive. Not reflexive. Irreflexive is different from not reflexive. Okay. For not reflexive, what do we say? We say if there is at least one element in A such that XX not in R, we say that's not reflexive. If there is at least one of them to be not in R. I mean, you have no relation from the member to itself. For example, if you have this, we say this is not an irreflexive, but it is not reflexive. It doesn't satisfy the condition for this one, but it satisfies the condition for not reflexive. Okay? Later on, اگر هاتو همو element كان هيج كاملة element كان لوب نبو بخوي هيج كاملة element كان x فيوندي نبو بخوي وا relate نبو بخوي أو بو relation أو تيد irreflexive بلام اگر هاتو چند دانه که فيوندي نبو بخوي أنا بلام هموش يعني نه لاني كم دانيك مع هيك فيوندي نبو بخوي أو كانت بوتري شيء not reflexive باشا وانت اگر هيج نبو أو irreflexive اگر هموي بو أو reflexive بلام اگر هني كان وابو هني كان لوك ما هبو هني كان نبو امان شيء not reflexive يعني انسى جوله ما هي يعني reflexive يعني irreflexive يعني not reflexive. Okay, so for not reflexive we say if there is at least one element in the set. Okay, which we have no the relation from the element to itself, we say that's not reflexive. Here is the example that we talked about. It says this relation on X is not reflexive. Why? The reason is here we have B in X, but we have no B and B in the relation. We also have C in the set X, but we have no CC in the relation. These are the reasons. Here we have some exercise that's for yourselves. It was the first property, and it said that's reflexive. Then the second one is symmetry, symmetric relation. For the symmetric relation, we say if we have AB, that means if A related to B, then we must have B and A. It means B must relate to A also. Again, هاتوا هر element depend هو element equal. أي بيشانه شو happens. For example, if you have 1 related to 2, so you must have 2 related to 1. Okay. So for all xy in X, if we have xy in the relation, we must have yx in the relation. We must have yx in the relation as well. And in the matrix notation, we say the matrix must equal to its the transpose, to its transpose. Do you know what's transpose? We just interchange rows and columns. همون can be column a bit transpose matrix again. I'm going to tell you how do you find the transpose of matrix. Look, this is the matrix notation. For this example, it says, is it asymmetric or not? Yes, that's symmetric. Let's find its transpose. How do we find the transpose of a matrix? We say the transpose is, we are going to write down the first row as the first column. Okay, this is the first row. We are going to change to the first column. Okay, we interchange rows and columns. So the first row becomes the first column. It becomes 1, 0, 0, 0. And the second row to the second column. So it's 0, 0, 1, 0. We just write down vertically 0, 0, 1, 0. Then the third one, the third column, the third row becomes third column. So it's 0, 1, 0, 0. We just write down vertically to column 3, 0, 1, 0, 0. And then for the last one, we have 0, 0, 0, 1. As you see here, we have 0, 0, 0, 1. We just write down it vertically and it becomes 0, 0, 0, 1. Look, if this equals to the matrix itself, it means the relation is symmetric. If these two are equal, we say the relation is symmetric. As you see, these two matrices are the same. In the first row, we have 1, 0, 0, 0. In the second row, we have 0, 0, 1, 0. In the third one, we have 1, 0, 1, 0, 0. And in the last one, we have 0, 0, 0, 1. So that's why we say these two matrices are equal. And this is the transpose. It equals to the matrix itself. That means the relation here is symmetric. We say a relation is symmetric if for all elements, for all V and W in the set X, if V relates to W, so we must have W and V, or we say W must relate to V as well. Okay, but if you have no relation between V and W, so we don't need to care about the relation from W to V. Look at this example. Here we have AA, BC, CB, DD. Okay, we have AA, so it's okay. But here we have BC, BC. We must have C and B. Do we have C and B? Yes. And DD, it's okay. That means this relation is symmetric, since if for all elements xy in the set, if you have A and B, so you also have B and A also. Okay, اگر هاتو دو element جواز ما بيبقى شو هم دو element همو دو element هيك جواز ليرة بيسمى هي أبد شيء شو هبه C و B شو هبه. So what if you have AD? We must have D and A also. Okay, so in the case if you have no D and A, we say that's not symmetric. But here, for this relation, we say that's symmetric. Okay, because in the relation, if we have AB, we also have BA. Okay, and here this is the matrix form of the relation, and you say it's symmetric, and it equals to M transpose. If this is M, so it equals to M transpose. You also can convert it from matrix form, then decide that's symmetric or not. Okay. You also can convert it for digraph, then decide. Okay. لا حالتي كانت تبقى باشتر تيجيشتو باشتر زاني كسيمتريك شيء ولا تحويلي كبو حالتي ما سي حالة ما سيت مان هي ماتريكس مان هي دايرة لها كامل كان باشتر زاني تحويلي كبو انجا بريال. And also we have anti-symmetric. For anti-symmetric, we say for all AB in A. AB, if AB in the relation and A doesn't equal to B, so BA doesn't belong to R. Or we say for all AB in the set A, if AB in R and BA in R, so A and B must equal. That means we must have only the elements which are equal. I mean, we have A and A, it's okay. It's possible if we have A and A. But if we have AB in the relation, we must have no BA in the relation. Okay? That means for anti-symmetric, we say we must have no any I mean, if you have AB in the relation, you must have no BA in the relation for all AB in the set. And in terms of digraph, we must have only one way arrows. We must have no any alternate arrow. For example, here we have A, B, and C. We must have only one way arrows. If we have any alternate arrow, we say that's not an anti-symmetric. Okay, we say that's not anti-symmetric. So for anti-symmetric, we say if AB belongs to R for all A and B in X, we must have no BA in R. This is the condition for anti-symmetry. It's similar to irreflexive, okay? In irreflexive, we said we must have no any loop from a point to a self. And here for anti-symmetry, we say we must have no any returned arrows in the diagram. Okay. And for the matrix, when you find its transpose, we must have 0 for each one. Okay. We must get 0 for each one. For example, here we say if we have 1, 1, 1. Sorry. This is anti-symmetric. Okay, this is anti-symmetric because all are going to be changed. All the values are going to be changed except the diagonal. We don't care about the diagonal. Okay, look, these are ones. When we find its transpose, those become zeros. If this is matrix M, then M transpose equals 1. The diagonal is the same, but here these elements become 0 and these become 1. As you see, these are totally changed. So we say if we get this, I mean, if all zeros become ones and ones become zeros except the elements on the diagonal, we say that relation is an anti-symmetric relation. Here we have an example. It says let R be a relation on the set defined as AB in R. If A is greater than or equal to B, we say AB is in R. If A is greater than or equal to B. Look, let's write down the set notation of the relation. You say R equals 1 is greater than or equal to 1. And you also can say 2 is greater than or equal to 2. 3 is greater than or equal to 3. And also 2 is greater than or equal to 1. 3 is greater than or equal to 1. We also have 3 is greater than or equal to 2. We have these elements in the relation. Converting this to diagram, we get this. As you see, for all non-equal elements in the set, we have only one-way arrow from each to the other. Okay, we have no any alternate arrows. ليه بهردو اللي مدك يكسان نبت تنها يك بيك أراس الروشتو أجا أراسي بيشوانش ما هبيت أو كاتنا بيت شيء anti-symmetric أبي بهميان يك أراس تبيت وأكريل اللي أما هاد نبت عسائية بلا نبي يك أراس زيادة هبيت. At most we have only one way arrow. It's possible if we have no arrows. So this is the diagram, and here this satisfies the condition of anti-symmetry. So we say this relation is an anti-symmetry because here we have AB in R, but we have no BA in R, and also that's for all A and B in for all A and B in X. For all A and B in X, if A doesn't equal to B, it satisfies this condition. So we say the relation is an anti-symmetry. Here we have another example. We have a relation R on X. X is the set of 1, 2, 3, and 4. Defined by X, Y, and R. If X is less than or equal to Y. If X is less than or equal to Y. This is the same as the previous one, but here we have 4 elements. But there we have 3. First, it's easier to write down the set notation and then converting it to matrix form. And even if you can directly write down the matrix form, it's okay. Here we have 1, 2, 3, and 4, 1, 2, 3, and 4, vertically and horizontally. For both rows and columns, we have 1, 2, 3, and 4, because the relation is from a set to itself, and the set is 1, 2, 3, and 4. Here, is 1 is less than or equal to 1? Yes. Is 1 less than or equal to 2? Yes. So we just put 1. If it satisfies the condition, we write down 1. If it's not, we write down 0. Is 1 less than or equal to 3? Yes. Is 1 less than or equal to 4? Yes. And then here, is 2 less than or equal to 1? No. So we just write down 0. Here, 2 is not less than or equal to 1. So that's why we just put 0 here. And then 2 is less than or equal to itself. So we just put 1 for that element. And for this element, we say 2 is less than or equal to 3. We just put 1, and so on for others. So this is the relation. And to find its transpose, if you find its transpose, and it's totally different except the elements on the main diagonal, we say that is, this is, let's say it's M, and so M transpose is, let's find M transpose. The first row becomes the first column. We just, this is first row, this first row. We are going to just make like this, and then to the first column. 1, 1, 1, and 1. And the second row, which is 0 and triple ones, we just make it to the second column. 0, 1, 1, 1. The third one, 0, 0, 1, 1. 0, 0, 0, 1. Look, don't care about this one, the main diagonal. But for others, this was 0 and it becomes 1. All are changed. Except these elements must all are going to be changed. Look, 0, 0, 0, 0. These all are 0 and all become 1s. And here, all are 1s. All become 0s. So this is M transpose. As you see, all elements are changed. That means the relation is anti-symmetric. That's anti-symmetric. Here we have this relation. R is AA, BB, C, and C. Look, here we say X is A, B, and C. On the set X, we have this relation. R is AA, BB, and C, and CC also. Is this relation symmetric or not? Is this symmetric? Is this relation symmetric or not? Let's find its transpose. If this is M, so M transpose equals to what? 1, 0, 0. This is the first row, and the second row 0, 1, 0, and the second row is 0, 0, 0. Okay, is this symmetric? Yes, that's symmetric. Yes, as you see, these two matrices are the same. We say if M equals to M transpose, then the relation is symmetric. That's symmetric. Is this relation anti-symmetric? Is this relation anti-symmetric? Let's check. Okay. Look, we say R has no members of the form XY with X doesn't equal to Y. We have no members here. I also can say that the relation is anti-symmetric also. It's both symmetric and anti-symmetric for this example. If we have only the relation between elements with their selves and no more relations, we say that relation is symmetric and also anti-symmetric. And also we have asymmetric. Up to now, we talked about symmetric and anti-symmetric. And now we have asymmetric. We say if for all AB in the set A, if AB is in R, then BA must not be in R also. We say here, if you have one way and no loops, that means we must have no relation between any of the elements with their selves, and also we must have no two-way arrows. Okay, we say MR must not equal to MR transpose. That means the matrix doesn't equal to its transpose here. But in the previous example, as you saw, the transpose of the matrix equals to itself. And it's also anti-symmetric. But here we say if they are not equal at all, we say that is asymmetric. What's the condition on asymmetric relation? We say if AB belongs to R, then BA must not be in R, and also AA must not be in R for all A in X. Okay, for all A in X. So it must satisfy this condition. We say we must have only one-way arrows in the diagram. We also must have no loops at any of the vertices. That's the condition. Look, here we say let R be the relation on the sets, which is 1, 2, and 3, defined by A is greater than B. A is greater than B. So let's write down the relation as the set form. We say R equals A to be greater than or equal to B. We say 2 and 1. Is it? 2 is greater than 1. 3 and 1. I also have 3 and 2. Do you have any other elements? No. This is the relation. If we draw the diagram for that relation, we get this. As you see, we have no loops at any of the vertices. We have no loops. And also, we have only one-way relation, one-way arrow. We have no returns at all. If we have only one returned one, we say that's not asymmetric. Okay? This is asymmetric. This is asymmetric relation. Because here we have 2 and 1 belongs to R, but 1 and 2 is not. 3 and 1 is in R, but 1 and 3 is not. And for 3 and 2 also. Okay? So if a relation satisfies these two conditions, so what if we have here, if we have 2 and 2 in the relation, what about that? Is that an asymmetric? Asymmetry, yeah? No, that's not asymmetry. This one. Because a relation from a point to itself, we must have no loops from any point to itself. That means we must have no relation from any point to itself, and also we say if AB in R, we must have no BA in R also. That's asymmetry. And also we have not symmetry. We have not symmetry. We say, okay, let's take a break for 10 minutes. We now have not symmetric. For not symmetric, we say if there exists AB, if there exists AB in A, in the set A, such that AB is in R and BA doesn't belong in R. That means if there is at least one way arrow, we say the relation is not symmetric. It's not symmetric if there exists AB in A, such that AB is in R, but BA is not in R. We say the relation is not symmetric. So we talked about symmetric, anti-symmetric, asymmetric, and also not symmetric. Okay. And you also have not symmetric and not anti-symmetric. If a relation satisfies these two conditions at the same time, we say the relation is not symmetric and also not anti-symmetric. Not symmetric and also not anti-symmetric. We say if A be any set, and if there exists AB in the set A, such that AB is in R and BA is not in R, and also there exists AB in A, such that AB is in R and A is not equal B, and also BA is in R. We say these two. This is the condition of anti-symmetry, and this is the condition of not symmetry. We say if a relation satisfies these two at the same time, these two conditions at the same time, we say the relation is not symmetric and also anti-symmetric. Here we have an example. It says we have this relation on the set ABC. On the set ABC, it's easier to write down the diagram. To construct the diagram, we have an arrow from A to C and an arrow from B to B, C to A, B to A, and A to A. We have these arrows. So here, we have B and A, but we have no, look, as you see here, we have an arrow from B to A, but we have no an arrow from A to B. So if there is at least one way arrow, we say that's not symmetric. That is not symmetric. So this relation is not symmetric, and also it's not anti-symmetric. Not anti-symmetric relation. We say a relation is symmetry is not symmetric and also not anti-symmetric relation if there is at least one way arrow in the diagram. If in the diagram we have only one way arrow, we say the relation is not symmetric and also not anti-symmetric. For the anti-symmetric, we said that we must have only one way arrow at all. Okay. We must have no any two-way arrows, but here we have these two-way arrows. That means this is not anti-symmetric. This is not anti-symmetric, and also it's not symmetric. Why? Because we have at least one way arrow. Okay. Here you have exercises that's for yourselves. in the third property of relations is transitive relation. It is transitive relation. We say a relation is called transitive if we have A, B, and B, C. We must also have A, C. That means if we have A, B, C. If A related to B and B related to C, we must have A related to C. We must have that. Okay? If we have A to B and B to C, so we must have A to C also. If a relation satisfies this condition for all ABC in the set, we say the relation is a transitive relation. This is the condition that I talked about. And in the matrix notation, we say if the matrix product of Boolean to itself, and we get itself, I mean the matrix itself, we say the relation is transitive. I'm going to tell you what's the product of Boolean. Look, this is product of Boolean. We say we multiply the matrices. We multiply the matrices. I mean the matrix to itself. Let's take a smaller matrix. It is 4 by 4. We are going to take 2 by 2. Okay, we are going to take 2 by 2 matrix, or let's say 3 by 3 matrix is better. We are going to take 3 by 3 matrix because 2 by 2 is not suitable for transitive. Let's say if we have, let's say 1 0 0 1 1 0 0 0 1. If we have this matrix, this represents a relation on the set X. Let's say it's M. What's the Boolean product of this matrix with itself? We say M. I'm gonna write down here. Here there's a space. If M to be 1 0 0 1 1 0 0 0 1. This multiplying by itself, M times M, M Boolean product to itself. We say times itself, 1 1 0 0 1 0 0 0 1. The product of Boolean, a matrix with itself. How to do this? What we do? Did you take multiplication of matrices? Okay. Here we did the same. We are going to multiply first row to each column in the second matrix. We're going to take each row from first matrix and we multiply it by all columns in the second matrix. So the first column in the first matrix is 1 0 0. It equals 1 and 1. We don't say 1 times 1. We don't say 1 times 1. We say 1 and 1. 0 and 1. 0 and 0. So you say 1 and 1. Or 0 and 1. Or 0 and 0. We say if you have 0, 0 and 0 is still 0. 0 and 1, if you have 1 0, it's still 0 also. 0 and 1 is still 0. But here, for 1 and 1, if both are 1, at only that case, we say it's 1. At only that case, it's 1. 1 or 0 or 0. If you have at least 1, and these are combined by O, or so it's 1. اگر هاتوا الان كم يجب ان يكبر ان جاء مكان كاتك بأور كوبسا أكاتو سنة يك أيجا زياتي يك بخريك. Okay, so this is 1. So this element is 1, and then we multiplied by the second column. Okay, 0 and 1. Look, 0 and 1, 0 and 1. Oh, 0 and 1. Oh, 0 and 0. This is 0. This is 0. This is 0 also. Because we said in only one case, it's 1. If both are 1. 0 or 0 or 0 is 0. So this element is 0. And then we multiply by the third column. 1 and 0. 1 and 0. 0 and 0. 0 and 1. This is 0. This is 0, 0. So it's 0 also. This for the first row. And then we do it for the second row. We write down the second row, and then we multiply it by all columns to the second matrix. Look, this is the second row. 1, 1, and 0. We are going to multiply it by all columns to the first column. We say 1 and 1. 1 and 1. Oh, 1 and 1. Oh, 0 and 0. Equals. This is 1. This is 1. And this is 0. So since at least we have 1 here, so there is, these are joined by all. It's 1. Okay. لبر أوي لا نكم يك يعني يكا فأول بيكو بس راون زيادتي ليه كشماها كات أنجام كده شكات يكات. So this element is 1. And then we multiply it by the second column. 1 and 0, 1 and 0. Oh, 1 and 1. So the result is 1 because we have at least 1 and okay. So it is the result is 1. And then for this one, 1 and 0 is 0. Here, 0 and 0, 0 and 0, 0 and 1. So it's 0. Then for the third row, for finding the elements of the third row, what we do, we are going to take this row 0, 0, 1, and you multiply it by all columns 0 and 1, 0 and 1, 1 and 0. Look here, 0. And then for the second one, 0, 0 is 0, 0 and 1 is 0, 1 and 0 is 0, so it's 0. And then 0, 0, 0, 0, 1, 1, so it's 1. We have this matrix. We say if the product of Boolean of the matrix form multiplied by itself, if we get the same, if it's the same, we say the relation is transitive. For transitive, we do this one. That's for only transitive. Okay. Look, are these two equal? Yes. That means the relation is transitive. That means the relation is transitive. Do you know how do we find this one? Product of Boolean in stats. Here we have an example. It says consider the following relations on the set 1, 2, and 3. Okay. Before we talk about the example, this is for the matrix form of the relation. But if we have the set form, we say if we have AB and BC, we must have AC also for all ABC in the set X. Here we have these two relations on the set 1, 2, and 3. R1 is 1, 1, 1, 2, 2, 3. 1, 1, 1, 2, 2, 3. And also in R2, we have 1, 2, 2, 3, 1, 3. It says which of them is transitive and which not. Here we have only 3 relations in R1. 1 related to 1, 1 related to 2, and 2 related to 3. Look, 1 is related to 2, and also 2 is related to 3. That means we have 1, 2, and 3. From 1 to 2, we have a relation, and 2 to 3 also. Do we have 1 and 3? We must have 1 and 3, and then we say that's symmetry. Do we have 1 and 3 here? No, we have no 1 and 3 in R1. So we say R1 is not transitive. It's not transitive because here we have 1 and 2, 2 and 3, but we have no 1 and 3. As I said before, I said if A related to B and B related to C, we must have A related to C. Here we have 1 is related to 2 and 2 is related to 3, but we have no A related to 3. That's why we say it's not transitive. How about the second one? So the reason here is we say since since 1 and 2 belongs to R and 2 and 3 belongs to R, I mean R1, but 1 and 3 doesn't belong to R1. This is the reason. That's why we say that's not transitive. And for R2, we say we have 1 and 2, 2 and 3, and 1 and 3. We have 1 goes to 2, and 2 goes to 3. And we also have 1 and 3. Okay? So here we say this relation is transitive. That's transitive. I'm going to just write down yes. Okay? This is yes, for the previous one, it's not, and we write down the reason why it's not transitive. And here we have given the matrix form of a relation. We have given this matrix form of a relation. It says, is it transitive or not transitive? We are gonna use Boolean product, the matrix with itself. The same as we did before. Look, this is the matrix. We are gonna find the product of Boolean, the matrix with itself, and we get this matrix. All these two matrices the same? This is the matrix. Are these two equal? Look, here this is 0 at this element, but here it's 1. All the elements must be the same. All the elements must be the same. And then we say those matrices are equal. If there's at least one difference between the matrices, we say that's not transitive. Here, this element doesn't equal to this one. So that's why we say these two matrices are not equal. That means the Boolean product, the product of Boolean of the matrix with itself doesn't equal to itself. So you say the relation is not transitive. The relation is not transitive. Here we have an exercise. Now we have equivalence relation. For the equivalence relation, we say if a relation satisfies a reflexive, symmetric, and transitive, we say that relation is an equivalence relation. We say a relation is an equivalence relation if it satisfies, if the relation is reflexive, symmetric, and transitive at the same time. Okay. Here we have an example. We have this example. R is a relation on the set 1, 2, and 3. It's 1, 1, 1, 3, 2, 2, 2, 3, 1, 3, 3. Okay. So let's write down first the matrix form. This is the matrix form. Okay, this is the matrix form. For reflexive, we said all the elements on the main diagonal must be 1. So it's reflexive. For symmetry, we are going to find its transpose. It must equal to itself. Okay, we are going to find AMR transpose. It equals to what? First row becomes, so for the reflexive, as I said, that's reflexive. So it satisfies the first condition. For symmetric, we say we are going to find transpose. It's 1, 0, 1. 0, 1, 0 becomes 0, 1, 0. Then 1, 0, 1. Is this equal to this matrix? These are equal. So it satisfies the second condition, which is symmetry. So the relation is symmetric. How about transitive? We are going to find the Boolean product. Okay. MR with the self. Let's find the Boolean product of MR with the self. We are going to multiply. We are going to find the product to 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. We are going to find the product of the first row with all columns, and then for the second, and so for the third. It's 1, 0, 1 equals 1 times 1, 1 and 1. Here we have 1. So the result is 1 also, because here we say 1 and 1, 1 and 1. Oh, 0 and 0. Oh, 1 and 1. At least one of the results is 1. So 1, 0, 1. If you combine these by O, the result is 1. 1 or 0 or 1, the result is 1. If there's at least 1 here, we say the result is 1. So that's why if we get 1, you don't need to do others. So here we have 1 and 1. 1 and 1 is 1. So you don't need to do 0 and 0, 1 and 1. So the result is 1. For the second row, 1 and 0, 0 and 1. Look at this, you can see we get 0. 1 and 0 is also we get 0. So the result is 0. And then for the third row, 1 and 1, we get at least 1. So the result is 1 also. We don't need to do 0 and 0, 1 and 1. So the result is still 1. And then we are going to pick the second row. The second row is 0, 1, and 0. 0 and 1 is 0. 1 and 0 is still 0. 0 and 1 is still 0. So we get 0 at all. So the result is 0. And here, 0 and 0 is 0. 1 and 1, look, here we get 1. So we don't need to do others. We just write down 1. And then for the third column, 0 and 1 is 0. 1 and 0 is 0. 0 and 1 is still 0. So the result is, we get 0 at all. So we get 0 here. And then for the third for the third row, we are going to take the third row 1 0 1 1 0 1, and the result is 1 0 1. Okay, if we multiply it by this, then by this, and then by the third column, we get 1 0 1. Are these symmetries the same? These are the same. That means the relation is transitive also. The relation is transitive also. So this relation is reflexive, symmetric, and transitive at the same time. So you say this relation is equivalence relation. And this relation is an equivalence relation. It's done here. I'm gonna clean this. It's better to convert the relation to matrix form and then working on symmetry, reflexive, and transitive. Okay? Because for reflexive, we say if all elements on the main diagonal is 1, we say that's reflexive. For symmetry, we just find its transpose is if it equals to itself, we say that's symmetric. And for transitive, we are going to find product of Boolean, the matrix with itself. If it equals to itself, we say that is transitive. And if relation satisfy these three, so the relation is called equivalence relation. So if a relation doesn't satisfy one of them, we say that's not an equivalence relation. Okay, it's not an equivalence relation if a relation doesn't satisfy one of these. Okay, this is the example. We have partial order relations. We say a relation on a set A is called partial order relation if it is reflexive, anti-symmetric, and transitive. There's only this change with the equivalence relation. So there is only a difference between partial order relations and equivalence relations. In equivalence relations, we say the relation must be reflexive, symmetric, and transitive. But here, in partial order relations, we say the relation must be reflexive, anti-symmetric, and transitive. Here we have an example. It says, let R be a relation on set A, which is 1, 2, and 3. And the relation is defined by A is less than or equal to B for all A, B in R. So the relation is this. This is the relation. For reflexive, we must check reflexivity, anti-symmetric, and transitivity also. For reflexive, here we have 1, 2, and 3. We have only 3 elements in the set. So we must have 1, 1, 2, 2, and 3, 3 in the relation. Do you have it? Look, 1, 1, 2, 2, and 3, 3. That means it's reflexive. That is reflexive. For symmetric, here we have 1 and 2. Do we have 2 and 1? No. We have no 2 and 1. We have 1 and 3. Do we have 3 and 1? No. We have 2 and 3. Do we have 3 and 2? No. Here we have only one way. We have only one way arrows. We have 1 and 2, but we have no 2 and 2. We have 1 and 3, but we have no 3 and 1. We also have 2 and 3, but we have no 3 and 2. That means all the arrows are in one direction. And if we write down the diagram, it's 1, 2, and 3. We have 1, 1, 2, 2, 3, 3. We have 1 to 2, 2 to 3, and 1 to 3. We have no any two-way arrows, but we also have loops. So this is an anti-symmetric relation. This is an anti-symmetric relation, so it satisfies these two. And for transitive, we have 1 and 2, 2 and 3. And do we have 1 and 3? Yes. And also, we have 1 and 2, 2 and 2. Do we have 1 and 2 also? Look, 1 to 2, 2 to 2. Do you have 1 and 2? Yes. It must satisfy for all 3 elements in the set. Okay. So here, the relation is also transitive. Since the relation is reflexive, anti-symmetric, and transitive, we say the relation is partial order relation. Okay. But if the relation is reflexive, symmetric, and transitive, we say that is equivalence relation. And it's the end of this part of the chapter. It's enough for today.